couple of places that we observe interference phenomena. Let's say we have water here and a slick of oil on top of the water. A light ray comes in. What happens? It's refracted toward the normal. It comes down, bounces off the water, hits the oil surface again, and it's refracted away from the normal. Okay, so some of the light comes through here and gets refracted along this path. Some of the light comes down here and gets refracted along this path. These 2 points are close together. The light from this point reaches your eye about the same time the light from this point does. But this light the light here has traveled further than the light here. If this is a thin film of oil, this thickness might only be 1/4 of a wavelength. If that happens, then the path difference down here and back will be 1/2 a wavelength, and the light here will be 1/2 a wavelength behind the light here, which means a peak of this will meet a trough of this, which means that you have destructive interference, and you won't see anything. You'll see a fringe. Now really what happens in oil is, it means that whatever wavelength of light happens to match the thickness of the oil is going to be damped out. It's actually going to be canceled out by the interference, but light of a different wavelength, which has a different color, will come through fine, and what you see when you look at the oil is a bunch of different colors. And of course you can observe that on oil slicks. You observe it all the time when you see oil slicks. Okay, another situation is where we have, let's say, 2 pieces of glass here, and I'm going to put a hair between these 2 pieces of glass, so there's a very small angle between the 2 pieces of glass. Now what happens is that light comes from outside, refracts into this glass, then refracts into the airspace, then back through the glass into your eye. Some of the light, though, doesn't go through the airspace. It just refracts off of this glass surface and gets back to your eye. So again, you have a path difference here. As that path difference, as you move from this point to this point along the glass, this path difference increases. It'll go from 0 to 1/2 a wavelength to 1 wavelength to 1.5 to 2 to 2.5 to 3 and so forth, maybe up to 100 wavelengths. And every time it goes through that complete cycle, it'll go through a cycle where the path difference cancels out the light, then where it reinforces, then it cancels out, then it reinforces. And what you see as you look across this glass is a lot of dark fringes with bright bands in between. And those, well, that's simply a diffraction pattern. Okay, Michelson Interferometer. Here we have 2 half-silvered mirrors, or this is a half-silvered mirror. Half-silvered means there's enough silver on it that half the light that comes into it gets reflected, the other half gets transmitted. It's of course not quite half because a little bit gets lost. This is a hunk of glass of the same type but without the silvering, and it's there just to compensate for the path difference between the glass. This is a mirror, and this is a movable mirror. This is a screw device. You turn the screw at the end and the mirror moves a little bit. This is a fixed mirror. It's mounted on a very heavy mounting. And what happens now? Monochromatic light of 1 wavelength comes in here. It goes here, gets refracted to this end of the mirror where the silver is. Then some of it gets reflected back here and goes up to this mirror and bounces back, comes back through the same point. Whereas some of the light transmits, goes through this thing, hits this mirror, comes back, and comes to this point. Now at that point, let's see, half the light got bounced off here and comes back, half the light got through here and comes back. So you got half the light coming back to here, half the light coming through here. No, I'm sorry. Yeah, no, I'm right. Okay, half comes back here, half comes back here. Now, half of this light gets reflected down here, and half of it goes on back along its original path, and half of this light comes down through here. So that what happens is this beam gets split into part that goes here and here, and into part that goes here and here, and then it gets recombined. So you have this combined beam. Now, part of the beam has traveled path 1, part has traveled path 2. Presumably, there's a difference in these path lengths, and if there isn't, there will be as soon as you turn this screw. As you turn the screw, you change the path difference. Every time you change the path difference by 1 wavelength, you get 1 fringe. Okay, I should explain that the fringes are observed by looking into a little telescope. Not going into the geometry of the situation, but what you see is little circular fringes, and as you move this, the fringes either expand outward or collapse inward. And of course, there's a fringe in the middle that disappears at some point as you move this thing. Or a new fringe appears in the middle and begins to expand outward. If you can count those fringes, and if you can move this far enough to measure the distance, if you've got a really good screw here, you can measure the distance by the amount of turn. You can even put a dial on this thing to tell you how far you've moved them there. And to do that, by doing that, you can measure the wavelength of the light, measure differences in the wavelength of the light, do a variety of things, determine distances here, and so forth. It's a very powerful instrument, and it was used in the Michelson-Morley Experiment, which was done real close to where I had my office in graduate school, real close to the physics building in which I learned undergraduate physics, and laid one of the great foundations for the theory of general relativity, one of the greatest experiments ever done. We'll talk about that at some point. You can read about it, the Michelson-Morley Experiment.